about this problem, how has been done.
Professor, did you share anything? Oh.
Huh?
Yes.
Share? Okay. Example 4-5. Okay.
Yes.
This is a generator, load 1 and load 2. So this one shows generator supplying a load. The second load is to be connected in parallel with the first one. Okay, the generator has no load frequency, so you have more than one generator. Shows a generator supplying a load. A second load is to be connected in parallel with this. Okay. While before switch is closed, the operating frequency, if after load 2 is connected. Okay, this is I think not exactly what I'm asking for. 1, 2 generators are maybe this one. Yeah. What are the examples? Yes, this one. Okay, this example I'm talking about. So there are 2 generators supplying a load. Generator 1 has a load frequency 61 and no load frequency has 61.5 Hz. And SP1 slope is given. Remember, slope might not be given. You can get it from the diagram. Here slope 1 SP1 is given 1 megawatt per hertz. Another generator 2 has no load frequency 61.0 and has the slope same slope. It can be different slope also. The 2 generators are supplying a real load totaling of 2.5 megawatt at 0.8 power factor lagging. Remember, this is already in watt. So, 0.8 power factor lagging is not important here. The resulting system power frequency or house diagram, okay, is shown here. Oh, it's not shown here? Okay. Question number 46. A is asking for at what frequency is the system operating, how much power is supplied by each of the 2 generators. So 2 generators are working, so you can think that frequency will not be will change if the load changes. Frequency is not fixed. Remember, frequency can be fixed with a infinite bus bar. Okay, when it is connected to the power system, infinite power system. At that time, you don't have to mention that frequency will not change. In this case, yes, frequency will change. So, if we look at this diagram, and slope is given, if you are asked to draw the diagram, this is the diagram. 2 generators. This is generator 1, this is generator 2. And they have no load frequency F no load 1 and this is F no load 2. That is given. Slope is given also. SP1 slope is given. It might not be given. You have to find it out using this graph or table. SP2 is given. Now they are supplying a load which is, this one is P2 and this one is P1. So total load is P1 plus P2 is given for total load. P1 plus P2 is given, I think 200 megawatts, something like that. P1, P total, and the formula is no load frequency is given for both of them So SP1 is given. Frequency, anyone can remember what is the formula? This is system frequency. This is no load frequency. This is for first one, P1. This is P1. Okay. This is for P1. And P2 is P2. F no load minus F system. System frequency for both of them is same. This is system frequency. System frequency for that load. Okay? System frequency. So this is the formula. You plug in all the values. SP1 is given. Then F no load 1 is given. F no load 2 is given. SP2 is given. So only thing is the total power is given by the bus bar. So you can find out F system. So once you find out F system, then you can also find out separately P1 and P2. So that's what the whole thing is asking. Look at this SP1. This is the formula. P2, SP2 is given. Total load, P load is P1 plus P2. And look at this. The amount of load in the question number 1 is 2.5 megawatt. So SP1 is given, which is the slope 1 megawatt per hertz, the 61.5 minus S system. So this way, system frequency is now 60 hertz. How much is P1? 1.5. How much is P2? Is 1 megawatt. You see, they are not sharing the same amount of power, even though it's close. All right. So what happens here? Suddenly, a total load changes. Suddenly, a load comes and 1 megawatt is added. So 1 megawatt is added, means total load is 3.5 now. You can apply the same concept and find out what is the new frequency. You might be asked what will happen. It will suddenly drop the system frequency. Look at this. System frequency, when another load is added, 1 megawatt load is added, is the system frequency drops. This happens only when you have only few of the generators working for the system. But if it is like thousands of generators works in power system, considering that infinite power supply is there, so frequency will not change. What will change? The amount of power your generator is sharing, that what might change if the system load is changed. So that's what might change for. Okay. What is this?
Professor, how
The
does
resulting power.
the power 1 and power 2 same?
Huh?
Why the P1 equal to P2? Like, why they're same?
Maybe why is it? Let me see. If no load governor set point Z2 is increased by 0.5 years. Okay, now let me see. If no load governor set point G2 is increased by new system frequency becomes okay. Let me see. Okay. Let me see the question number 3. Yeah, what it says, with the system in the configuration described in part B, what will be the system frequency and generator powers be if the governor set points of G2 are increased by 0.5 hertz. Okay. If the governor set points on generator 2 are increased by 0.5 hertz. Okay. So this G2 generator 2 has been increased. So let me see what they are saying exactly. So Okay, okay, see. The SP1, 1 megawatts, 1 megawatt per hertz, it's fine. It was one, okay, slope is 61, no load 61.5. Oh, it says no load frequency has been increased. It didn't say the system frequency didn't change. No load frequency has been changed. Okay, what it says,
So if
okay,
the
what
load
will
frequency
happen
is same, then
if you increase this one,
Mhm.
no load frequency, if you increase this part, and as you know the slope is same, so you can geometrically you can prove that their power sharing would be same if these two lines are have the same slope, right? You can
Yes,
prove
yes.
anywhere it goes they are sharing the same amount of power, right?
Yes.
So that's how it says, because it says that okay, no load frequency. So no load frequency is also is important. That what is the no load frequency? That means governor set point this one where you are setting up, starting from the no load. So when they are same and the slopes are same, it will not be same. You can try if the slopes are different.
Yes.
Slopes are equal, no load frequency are equal, so they have to share same amount of power in every case. Okay, that's what happens here. You can check. Look at this 61.5, 61.5. 1 megawatt per hertz, 1 megawatt per hertz. That's why they are same expression. You see, express same expression.
Yes.
So this question might be asked like this way: if you want to share the same amount of power, what should be the no load frequency of each one? Something like that. Even you can equate them by changing if the slopes are different, you can also equate them. So any questions so far? This is parallel operation. So parallel operation, you can get a different types. Like slope, you might need to find it out. This slope is megawatt. Don't think that it is reactive power. It is not reactive power. It is real power. So you have to know the real power instead of reactive power. If S is given, you need to find out the real power. Okay. So if you are given S and theta for lagging or leading, you can find out the real power. So you need real power, then you can find out the slope and you can find out all others also. Any questions so far? Okay, let's look at another problem example. Remember the formula to make a maximum power, power, what you have to do, this is one. This is the formula that you need to use. What is that? Okay. Let's do one more problem from this chapter. 4.3. We have done 4.3 before. 4.2. Here, this is a very good problem in this. Okay. 480 60 Hertz Dell connected 4-pole synchronous generator has open circuit characteristics shown. This one, open circuit characteristics from here. The generator has a synchronous reactance. XS is 0.1 ohm and armature resistance RA 0.015 ohm. The full load, the machine supplies 1200 ampere at 0.8 power factor lagging. Under full load condition, friction and windows losses is 40 kilowatt and the core losses is 30 kilowatt. Ignore any field circuit losses. What is the speed of rotation of the generator? As you know, this is synchronous generator, so rotor speed and the flux speed is same, 120 F over P. So all the information will be is given here. Is 120, F is 60, P is number of poles is 4. So you know the rotation speed of the generator. How much field current must be supplied to the generator to make the terminal voltage 480 at no load? So it's no load characteristics. E, they are asking for E. They are giving you E at no load 480 volt for Dell connected. So line, this is always a line voltage characteristics, open circuit characteristics. So what is the voltage here? No load voltage is 480, and this is no load voltage characteristics, open circuit characteristics 480. You have to go back to see what is the field current units, around 4. 4 is how much? Yes, and 4.2 or something. This is what you have to, you can assume, but you should draw like this in the test when you will be given this kind of graph. So you can just, okay. What you can do, you just draw hand, sketch like this. Okay, so 480 and write down here the value. So write down 480 volt and field current 4.2. So 4.2. I do not expect that everyone will have the same value, because this is something that you guess. Okay, 4.2, 4.18, whatever 4 points, you can get the field current. This is field current. So because of this field current, you can get the equation looks like this, the circuit looks like this. This is field current. It field is in rotor, and then that will produce a voltage E here, which is, this is Dell connected, so this is also line to line voltage, so 480. And they are asking how much is the field current to produce 480 here. That is 4.2. 4.2. Okay, so let me see the answer here. Okay, so you have the frequency. You can find out first they're asking how much is the speed, is 1800, 120 F over P. So you can get the RPM. This is synchronous speed, okay, and the shaft speed as well. So you can get the first one, terminal voltage and phase voltage is same. At no load voltage, IA is 0, EI is V5, whatever, 4.5. They pick 4.5, the flux current, from here, 4.5. Okay, as considered as 480. Now, question B says, question A is done. No load voltage field current you can find out. Then if the generator is now connected to the load and the load draws 1200 ampere, which is full load, 0.8 power factor lagging, how much field current will be required to keep the terminal voltage equals to 480 volt? What does it mean? This is important. This is important. You see, terminal voltage is now 480. It was before no load voltage. Now you have a load. Still you have output voltage, terminal voltage is how much? 480. Meaning that, look at this, you have a circuit here, RA, all are given XL. Now you have a load. This is no longer E because terminal voltage is 480. This is Dell connected, that's why I'm writing 480. If it was Y connected, what would I have written? 480 divided by square root of 3. This is Dell connected. Now this is not terminal voltage. Sorry, this is not E. This is V phase. Okay, V phase. This is constant now. So this is the way you can explain whether it is V phase or terminal E. V phase or E. So you know that this is V phase, and you know the current 1200 ampere and you know the theta also from power factor lagging, and times RA, and XS is given also, XL, XS, RA, and you can find out E, voltage E here. Okay, once you know E, remember this is del connected, so this is line voltage, and you can go back to find out to the OCC for that voltage. Say E is now 500, so look at E is 500, so look at 500 and see what is your field current here. Okay, so that is what they are asking. What would be field current if your terminal voltage V phase is for it, not the E is for it. Now this is what we have to do. Look at this here. Where is that? Okay. So you find E, V phase is 480, RA you know already, IA is how much? Okay, so IA is how much? 1200 RPM, 1200 ampere, but it is del connected. Your circuit, in this case, this is also important to be careful that this circuit you are working with, this is del connected, so your IA is different now. IA is 1200, but for del connected, always given current is line current until and unless is not given. So line current is 1200. So phase current, you are dealing with phase circuit. So your current is 1200 divided by square root of 3. So IA equal to 1200 divided by square root of 3. And then you can start your work. So you need a little bit careful that when you need this square root of 3 to divide for your single phase equivalent circuit. Here in this case you need to work with current. Now look at this. This is the current, phase current. Now if you have the phase current, you know how to go find out EA using this formula, and the power factor is still lagging 36.87 degree, and ultimately E is 532. Go back to the chart, OCC, and directly you can get. Remember, if it is Y connected, you cannot go directly from E. If it is Y connected, then if it is Y connected, then you cannot go directly. What you have to do, say if it is Y connected, you found E is some amount, so 300. If it is Y connected, then you have to make it for three-phase line-to-line voltage. Then that is the voltage. You can look at the graph, because graph always gives you the line-to-line voltage OCC. OCC is never meant for single phase equivalent. OCC is meant for three-phase equivalent. Okay, three-phase circuit. So what is the line voltage OCC is mentioned? So this is for line voltage at no load situation. So you find out that voltage and you can find out the field current. Okay, so this is what they get. Now power by the generator and all this other question. How much power the generator now supplying? Okay, generator is now supplying. How much power is supplied to the generator, to the prime mover? Okay, what is the machine's overall efficiency? So how much power is supplied to the generator by the prime mover? Okay, and how much power is generator now supplying? Okay, so it's just a little bit of technical word. How much is the torque? If you know the all losses, you can find out how much is the prime mover power. Okay, at the beginning, what is exactly given to the shaft. Then how much generator is the converted power. Let me draw again the differences between them. Okay. So this is Sorry, this is the generator. So the generator is getting power, converted power is here. So this is generator power and prime mover power plus all the losses before. Okay, so E times I cosine of del. Remember, it's single phase equivalent. EI cosine of gamma here. What is the angle between them? Then EI cosine of a gamma. So if you draw V phase circuit, this is, remember, this is not this, so you have to have a angle. So this is V phi, and this is E, and this is I is lagging, so the angle between E and I is gamma. So what is the power here? In the converted power or generator power, EI cosine of gamma. EI cosine of gamma is the power here. VI cosine of theta is here, the power output. Whatever the power here, you can also add the stator armature copper loss, then you can find out converted power, or EI is cosine of gamma. Once you know EI cosine of gamma, that is the power, a converted power, then you add all the other losses that is mentioned one by one. Then you are at the shaft, and you can find out the shaft power. And then if you divide by shaft the power divided by omega, you can find out the shaft torque. So that's what they have done here. If you look carefully, this is output power, VI cosine theta. Then this is the generators giving this amount of power to the load, supplying, okay. The power that the generator is now supplying. Hello? Hello? Walaikum salam. All right, now okay, this is the generator is supplying to the load. Okay, supplying found in the load. So you can find out this is output power. Square root of V, you know, line voltage, you know, line current is 1200, line voltage is 480. Square root. This is the formula you just need to know. If you find in phase voltage, phase current, and then you times 3 cosine of del, you will get the same. So what is the shaft power? All you add. So this is what electrical loss. This is armature copper loss. You know RA, so you can find out I square. I, you know, already is 692. It comes from 1200 divided by square root of 2, the square root of 3. That is the armature current. I square, you know RA, then you times 3. Why you are using line current? Because armature resistance is for single phase equivalent resistance. So you have to use as a single phase current, phase current, then resistance I square R times 3. So that is the electrical power, copper loss plus all the other losses. That is what input power. Then output over input power is this. Any questions so far?
Professor.
Yes.
The midterm will have 3 questions or 2 questions?
3 questions.
And you have homework for this chapter up, right? For submission?
Yes, I already uploaded that. And I also uploaded the day of exam, the project also, project 2.
We have 2 projects?
Second project, okay? Yeah, on generators. 5 points, and your participation is 5 points.
And Professor, is the project group or single?
Single, alone. Please, if you have any questions, anything that you don't know, I have office hour on Sunday, Monday after 10:30. you can send me an email. We can set up the time if you need any help. Okay, I will be in my office hour. I will use Zoom in that case. Okay, if necessary. You can send me email if you want to get any help. If you need any help. Okay. All right, for today, I have another class after this. And if you have